The third law of thermodynamics says that the entropy of a perfect crystalline substance, okay, all perfect crystalline substances, their entropy approach the same value as the temperature approaches absolute zero. And so as a matter of convenience, we're going to assume that that same value that they approach is zero, okay? The implication of the third law is that if you're looking at reactions and you want to know what the delta S for a reaction is at 0 Kelvin, then you can just say it's going to be 0 because all substances will have the same entropy at 0 Kelvin. Then the delta S, the change in entropy when the reaction happens at 0 Kelvin, if it were to happen at 0 Kelvin, would be 0. Like I said, as a matter of convenience, we define that to be 0. So the standard entropy, okay, remember that's the difference between the entropy at 298 Kelvin and the entropy at 0 Kelvin. Then that's also known as a third law entropy or the absolute entropy. Okay, so it's also known as a third law entropy because you can say that's the difference between the entropy at 298 and the entropy at 0 Kelvin is just the entropy at 298 because we're assuming the value at 0 is 0. Okay? So application of the third law is this. It allows us to calculate delta S for a reaction, where you start with reactants at 298 Kelvin and end up with products at 298 Kelvin. So what we do is this. We imagine cooling your reactants from 298 Kelvin to 0 Kelvin. What's the delta S for that step? The delta S for step 1, okay, this is step 1, would just be 1. It's just the negative of the entropy of the reactants, right? Negative of the standard entropy of the reactants. Okay? Then if we imagine that we have the reaction happening at 0 Kelvin, what's the delta S for step 2? What does the third law say? Delta S for step 2. A reaction at 0 Kelvin, delta S is 0. Okay? Now that we've converted the reactants to products at 0 Kelvin, okay, so our reactants are now converted to products at 0 Kelvin. We now imagine those products at 0 Kelvin. You heat them up so that we end up with products at 298 Kelvin. So we go down to 0. Okay, your reactants go down from 298 Kelvin to 0. Change them to products at 0. Bring them back up to products at 298 Kelvin. Delta S for step 3 would be 1. It's just the entropy of the sum of the standard entropies of the products. So negative entropy of standard entropy of reactants plus 0 plus the standard entropy of the products, and so that allows you to calculate delta S for reaction. Okay? And you can look up values of standard entropies from tables. So you can calculate the delta S for any reaction as just the entropy of the products. Okay? You can see it's just the sum of the standard entropies of the products minus the standard entropies of the reactants. That will give you the delta S for a reaction. Okay? So let's calculate the delta S for this reaction. You need to look up a table of standard entropies. Okay? And unless otherwise specified, we're interested in reactions happening at 298 Kelvin. Okay, so let's look up, where can we look up delta S values? A good source would be the back of your book. There's a table there. Or you can go to webbook.nist.gov. Okay. And then click on NIST Chemistry Webbook and you do a search. So what are we interested in? NH3. So we look at gas phase data for NH3, ammonia. And if you look at entropy, standard entropy of a gas at 1 bar is 192.77 joules per Kelvin per mole. Okay? So for ammonia, it's 192.77. So for this one, it's 192.77 joules per Kelvin per mole. What's the standard entropy of H2? Let's do a search for H2. Oops. H2. Hydrogen. Standard entropy of H2 is 130.68 joules per Kelvin per mole. 130.68 joules per Kelvin per mole. Okay? And we do the same thing for N2. Let's do a search. Search for N2. And that's nitrogen. And what's the value for nitrogen? It's 191.61. Okay? Joules per Kelvin per mole. 191.61 joules per Kelvin per mole. So what's our delta S? What's the formula for delta S? Entropy of the products minus entropy of the reactants. So standard entropy of the products minus the standard entropy of the reactants. And so what would those be? What's our product? Ammonia. We have 2 moles, okay? So 2 moles of ammonia times 192.77. Okay, let me fix that. 2 moles of ammonia times 192.77 joules per Kelvin per mole. That's your entropy of your products. Minus entropy of, so this is products right here, your ammonia. Minus for the reactants, what is it? 3 moles of H2. So 3 moles times the entropy, standard entropy of H2 is 130.68 joules per Kelvin per mole. Okay. Plus, so that takes care of hydrogen. And nitrogen is 1 mole. So 1 mole times 191.61. 1 mole of nitrogen times, what was that? 191.61 joules per Kelvin per mole. So mole cancels out. So what's the answer? Someone calculate that for me. Two times 192.77 minus 3 times 130.68, okay, minus 191.61. That's a delta S of negative 198.11. Okay. Negative 198.11 joules per Kelvin, okay, per mole of reaction. So negative 198.11. That's the delta S for your reaction. You got that? The delta S for this is negative. Negative, what was it? 198.11 joules per